So you think it's an advantage to be taller when running a 100-meter race. To test this, you obtain the heights and race times for 20 people, and the data is in this file for download. So we're asked a series of questions based on this data, the first of which is to look at making a scatterplot. We're then going to do some regression analysis, looking at predicting the race time based on height, seeing if that relationship is actually in existence, which is part 3. Then we're going to describe how adequate our model is, and finally we're going to predict the time that a 165 centimeter person would run based on using this model. So let's go to the first step, which is looking at creating this scatter plot where we want to plot height against race time. So jumping across to Excel, this is my data. So we're going to be plotting a scatter plot. So I'm going to highlight all of my data here and then go insert. And one of the chart options here is scatter, and I'm just going to pick the one that gives me dots like so. So Excel has automatically picked up height as being the variable that goes on the x-axis here. If you want to label it, it's as simple as going to add chart element, axis titles, and that would be the horizontal axis. So I can pop that in here as being the height. I'll put centimeters on the end as well. And then for the y-axis, that is race time. So again, let me go in and add a title to it here. So this is going to be the race time in seconds. So just remember that this variable here, which I've got as height, which is on the x-axis, that is my independent variable. I can pop that in brackets here. And then the one that I am predicting, that is the dependent variable. So I'm going to be using height to predict race time. So this one here is dependent. Cool. Alright, so looking at this graph here, it doesn't look like we have an overly strong trend between race time and height. All our points, they look a little bit like scattered. However, if we were to fit a trend line through it, I feel like it would be kind of downward looking. And if we want to, we can actually do that with Excel. If you go into Chart Tools, go Add Chart Element, one of them down here is trend line. So if we pop that in, it's not very good colored at the moment, but it's this line here that's dotted in, and it is trending downward. So what that's telling us is, as our heights get bigger, our race times get smaller, so therefore taller people do look to be running faster based on this data. However, as it's a bit scattered, we might want to quantify how good we think our fit actually is. So anyway, regardless, that's the answer to the first part of the question of doing our scatter plot. So the next part of the question, if we jump back, what we want to do is find the actual estimated regression equation, and we're going to do this using Excel. So one way to do this is using the data analysis tool in Excel. So let's click on that, and what we want to go down and find is the regression here. Click OK. So now we need to give it the x and y data. So the y data, this is your dependent variable, which we said was the second column here. So let me highlight that. And for the x range, that was our independent variable, which is the first column here. So that's all good. I'm going to tick the first option here for labels. That's just saying that we have basically titles on each of our columns, which is true. None of these others need ticking other than the output range. So this is just where it's going to appear on the spreadsheet. So let me pop that in. Let's say we put it here. And if we click OK, this is our output of our regression. So the main thing that we're looking at for this answering part 2 of the question, which was to find the estimated regression equation, is we need the coefficients. So if we look down, it's in this very last bit of the table here. We've been given the coefficients. So the intercept of our equation is 25.86, and the height is negative 0.067 approximately. So let's go over and write that out as an equation. So this is for part 2 that we're doing. So our regression equation is of the form y equals BO plus B1x, because all we've got is one dependent variable. In fact, you always only have the one dependent variable, but only one independent variable as well. So we said our dependent variable here was going to be the race time. So we can pop that in. BO, that was the constant that came out of Excel. So that was the 25.86. We've then got B1. This was the constant associated with our independent variable. And that was, in fact, it was a negative number, 0.067. And X, that was our independent variable, and that was of course the height of the person. So that there is essentially our answer to the second part of the question where we've predicted this regression model. So part 3 is now to test if there is actually a relationship where taller people run faster. So if we look at this equation, what we're really interested in is kind of this B1 value, all right, the coefficient for our height. So what we've found here is that it's a negative number, which would suggest that race time here is going to get smaller as height increases. So it does appear that there is, at least in some sense, a relationship where taller people run faster. But what we want to do is test this in a more rigorous way, which is like using our p-values. So what we're going to have is essentially a null hypothesis and an alternate hypothesis that we're going to test. So the null hypothesis is essentially that this B1 value is equal to 0, because if it's equal to 0, then that means that there is no relationship with height or our independent variable. On the other hand, what we're interested in is whether the taller people run faster. So if taller people run faster, that means that our B1 value here is going to be a negative number. So I'm going to write this as B1 is less than 0. So that's what we're testing. So this here is no relationship between race time and height. And this one here is testing whether taller people are faster. And we can go through our normal process of doing a hypothesis test, where we have our level of significance, we calculate our p-value, and based on comparing our significance level and our p-value, we can decide whether to reject or accept our null hypothesis. So let's say here that we assume our level of significance alpha is equal to 5%. So in that case, if my p-value ends up being less than 5% or less than alpha, I'm going to reject my null hypothesis. In other words, I'm going to say that there is evidence for taller people running faster. If the opposite happens, so the p-value ends up greater than alpha, then we're going to accept HO. In that case, there would be no statistically significant evidence for a relationship between height and race time. Alright, so we let Excel do the work in calculating the p-value. So if we jump back to our analysis here, what we should be able to look across to is this column p-value, and we're interested in it for height. Okay, so that's the cell we're looking at. And Excel automatically calculates the two-tail p-value. So that's what this is. So just pop that here. Now we are testing to see if it's basically a one-tail test. So B1 is less than 0. So if we want a one-tail test, essentially all we do is halve the value that Excel gives us. So it's going to be this number divided by 2. So we've ended up with a p-value of about 0.02. Now, if I jump back, if our null hypothesis was B1 does not equal 0, this would have represented a two-tail test. Okay, because we're looking at both directions. So B1 might be less than 0 or it might be greater than 0. But since we're just looking at one direction here, we are doing a one-tail test. So let me pop over here. So based on this analysis, we've ended up with a p-value. It was about 0.02 for the one tail. Oh, let me pop that in. So now we should be able to make our conclusion on whether to accept or reject our null hypothesis. So 0.02, that is less than 5%, which in decimal form is 0.05. So that means we've fallen into this first option here, which means that we are going to reject HO, and that means that we're going to accept instead H1. So therefore we have some evidence that taller people run faster. Okay, so that would be the answer, to part 3 there. So moving on to part 4, now what we're looking at is the overall adequacy of the model. So jumping back, again we let Excel do this for us. What we're going to be interested here in is like either the R-square or the adjusted R-square. Alright, so both of these essentially are measuring the same thing. The adjusted one is a little bit more accurate. It takes into account how many independent variables you had, and which changes, I guess, the number of degrees of freedom here. And yeah, makes it a bit more accurate in that sense. But really they're measuring the same thing. Remember that R-squared can vary between 0 and 1, where 0 is the worst possible fit ever, and 1 is a perfect fit. So let's say we pick out our adjusted R-square value. We've got 0.17 approximately. So this is definitely on the lower end of a quality fit. Okay, it's closer to 0 than it is to 1. So if I jump back over to my working here. So for this part 4, we've got R-squared is equal to 0.17, and I should pop that's the adjusted R-squared. So my comment will probably be around the fact that only about 17% of the variation in the dependent variable can be explained by the independent variable. So in other words, only about 17% of the time that someone gets can be explained by their height. So this isn't a particularly good fit, but it's, okay. It should be enough to make some predictions between those two variables. And it kind of makes sense that it's not particularly high because there's a lot of other factors that are going to go into how fast someone can run, such as how much training that they do, perhaps also their gender would be a significant factor. So yeah, it makes a lot of sense that we only get a small R-squared when we're only looking at height and race time. Alright, so let's move on to the last bit, which is part 5, and here we're asked to predict the time of a 165 centimeter person, using our model. So if we go back to our regression equation, we had that race time was equal to this equation here. So I'm just going to copy that onto our other page. So race time was equal to 25.87 minus 0.067 times the person's height, which of course was in centimeters. So if we're looking at the height of 165, we should substitute that into our equation. So 165 goes here. And if you type that into a calculator, you get about 14.81, and the units for that are seconds. So that's how fast we would expect someone to run if they were 165 centimeters tall using this model. So that's pretty much all there is for this video, and I'll see you in another one.